FoodAtlas, an AI-driven knowledge base of food, chemicals, and health effects, presented by Dr. Ilias Tagkopoulos, Director, AI Institute for Next Generation Food Systems, AFES, Professor, Department of Computer Science and Genome Center, University of California, Davis.
My name is Steve Brown. I'm the Associate Director of AFES, also known as the AI Institute for Next Generation Food System, funded by the U.S. Department of Agriculture and NIFA. I wanted to let you see, there we go. Know a little bit more about AFES before we get on with our introductions here. AFES has as its mission building a better food system with AI and a healthier society and a more sustainable planet. We have an ecosystem of 100+ academic and industrial partnerships, and we also have sub-awardees at Berkeley, Illinois, Cornell University, USDA ARS, and University of California Agriculture and Natural Resources. We have, over the years, funded 40+ projects related to AI and agriculture. You can go to our website and learn more about them. These are our impact numbers. We've funded 51 teams plus, $60 million plus in leveraged funding, 150 papers published, and supported 60+ faculty. We also have a lot of events including hackathons, seminars, outreach events at like the Ag Robotics Conference and whatever. So we have reached 2,000+ attendees at our events and trained 1,000+ students and 70+ industrial partnerships. So with that, we're going to launch into our speaker series, the final one of our fall season. And it is my pleasure to introduce my director, the director of AFES, Ilias Tagkopoulos. Ilias is a computer science professor at UC Davis, leading the integrative biology and predictive analytics lab. He is also, as far as his background, received his bachelor's and master's in electrical and computer engineering at University of Patras, and a master's degree in electrical engineering at Columbia University, and finally at Princeton, a PhD in electrical engineering. So with that, it is my pleasure to introduce Dr. Ilias Tagkopoulos.
Hi, everyone. It's also always impressive to hear others pronounce my name. I'm thinking of changing it to Vladimir Tagopoulos. Okay, so thank you for coming. It's always very nice to see so many new faces, and a lot of you have contributed. By the way, when we see these numbers, right, when we started 4 years ago, we never even had in our mind that this would be actually possible. And this is because of the amazing work that has been done by our faculty, our students, and our staff. And I would like actually to just recognize them and applaud exactly those people. We're in the 4th year running AFES. Thousands of students have been supported, 50 to 100 faculty involved and actively funded. And one of the most important things that we're doing in AFES is being able to educate not only our constituents, not only the practice, the stakeholders and the practitioners, but also our policymakers, the senior staff, the senators, both here in our state and in Washington. And this is something that we need to continue doing in order to make sure that AI is both responsibly developed and also in the hands of the many versus the few. So with that, today I'll talk about FoodAtlas. But this is bait and switch. I'm not going to talk so much about FoodAtlas. I'm going to talk about evidence synthesis and how we can have a better tomato. I would like to think what you ate today, what you ate yesterday, and tell me, first of all, are you happy? Are you happy with your choices? Let me see. Do you think you ate healthy? It was a good, healthy meal. Let me see hands. It was your meals, the choices you are making, are they healthy? Yeah? Yeah, so half of us, right? Do you think you have the information you need in order to make healthy choices? Not so much, right? do we really know what those foods are doing to our body and mind? Like, if you look at the chemicals that are in those foods, what percentage do we think that we know? Like, an estimate would be actually what was published 3 or 4 years ago is 2%. I would say now we're better at 5 to 10%, but that's it. 5 to 10% of what is in our food is known. When we're going into what it does to our body, even less is known. And we're talking about like 2024, right? So many years and millions of dollars in terms of nutrition science, food science, and still it's not the dark ages, but we have so much more to know. So what we do here is try to collect that knowledge that's out there, hundreds of thousands of papers, raw data in data sets, databases curated by a lot of people with grit and perspiration and inspiration, and put that all together in what we call evidence synthesis, getting all that evidence and having a single source of truth of what's in our food, what it does to our body, how it's related to health, and other aspects, for example, flavor or sustainability for our planet. Okay, so to start, I'll spend like 3 or 4 minutes on the science behind it, so we're all on the same page. And apologies for people who are in computer science, have done this many times before. Just enjoy your food while we're doing that. So some background. This is a neural network. The neural network has inputs. This is the input layer. It has the hidden layer, which is the middle, this intermediate layer. It can have 1, 2, 3, 4, 10 intermediate layers, and it has an output, and the output is here. So this is a neural network with 1 input layer, 3 hidden layers, 1, 2, 3, and the output. The fundamental unit of a neural network is this circle here. It's the node. We call it a neuron. And the reason we call it a neural network is because the whole concept, it actually approximates, and it comes from 1950s, approximate what happens in our brain, right? We have the neuron, we have some inputs through the dendrites, right? Synapses, and you have an output, which is this electric pulse signal that's being generated. Same here. This node that you saw before has some inputs, x0, x1, x2, xn. It calculates a function. It can be very simple. It's just a weighted average, for example. And it has an output. The output can be 0 to 1 or anything else. Okay. So with that very simple concept of a neuron, or perceptron, as it was called in the 1950s, we can create the representation of any possible function. What we need is many of those layers, many of those neurons, in a way that all collectively is more than the sum of the parts. Okay, when we do that, and this has been done over the years, when we do that, the question is, how do we associate the variables within, right? Like, what exactly neural networks learn from the data once you do that? Well, it's the same thing as humans. What we do, if you think about it, is we associated variables. When the weather is good, it's gonna be sunny, it's not gonna rain. Whether there are clouds in the sky, there's a 50% probability of rain. So we associate clouds with rain, right? We do the same with our food, and this is how we evolved, right? There is an AFI seminar, it's gonna be, what do we have? Panda Express, so let's go, right? Or pizzas or whatever, right? We associate things. This conditioning is central to how we think and who we are. So the same thing here. It's just association between the variables, that's all. But they are doing it billions of times, not just one or two. And this is where this amazing power comes from. So how do we encode text? Okay, I understand if it is temperature, continuous variable, it's going to be 80 Fahrenheit, 82.5, etc. I get it. I give a variable that is a numerical. The neural network will process it. It will have a function. They will have another variable at the output, which is also a number. That I get. But how can we go from text or images into an output? This is where embedding comes in. So what we do is we associate words with a vector, a list of numbers. And this we call embedding. Okay? So it is, you can imagine it as a location system, like a coordinates, like the way we have it like in Google Maps, and you have the GPS coordinates of the different shops, of the different streets. It's exactly the same with this being the GPS coordinates, and this is the name of the shop. Okay, good so far? Well, if we do that, and if we have the right GPS coordinates, then now we can cluster things together. We can associate variables. We can do algebra here. For example, man and woman will be close, right? As king and queen will be close. Not only that, but if I take the distance between man and woman, I want to be the same as the distance king and queen. And you can do anything else. Man to king should be woman to queen, for example. And then the question is like, okay, good, but how do you know what the GPS coordinates are? Well, this is where you have different neural network architectures that you are feeding in a lot of data. In this case, it can be Wikipedia. It can be Shakespeare. It can be, the anatomy of man and woman, of humans, right? And by reading it, by actual associate, initially it will be totally off, and slowly will be converging something that makes sense. If we do that for food, this is how it looks like, our food. So here we fed papers, Wikipedia, etc. And the neural network figured out, associated different foods and placed them in this space. So this is an atlas of our food based on, well, the relationship with Wikipedia, for example. Good. So how do we represent this? There are two ways of representing it right now. One is creating this knowledge graph, this network, as you saw it here. And the network is, for example, Eiffel Tower is located in Paris. Paris is the capital of France. This is a knowledge graph, right? It's a network of knowledge where nodes are of different types, can be places, can be people, and edges are relationship, father of, president of. And there are many of them, right? For everything we do, we can actually create a knowledge graph behind it. Over the past 7 years, we have something that's called a large language model. Everybody has, played with ChatGPT, unless, you're not, you just wake up. ChatGPT and all these large language models, all these bots, that they are doing amazing things. Again, all they do is learning how to associate those variables. This is the architecture of a large language model, something like ChatGPT. And ChatGPT is part of this, by the way. So the inputs come in. These are words, sentences. There is this embedding that we learned from here, this one, the coordinates. So the first step is actually, I will now learn how to map the words like man, woman, etc. And then I'm doing some processes. We don't have to go into details here. But what it does here is learning how to associate. If I'm asking a question, what should be the right answer? Okay? So first, we're taking the words. Second step, we're now associating with GPS coordinates. Third step, I'm able to do any kind of calculation that I train it to, which is here. And fourth step is I'm reproducing the answer in a way that you understand. So I may get coordinates at the end, but you want words. If I ask you, Barack Obama is man or woman, you don't want like 2.3, 3.2, etc. You don't want that. You want it's a man. Okay. So these are the steps of processing in a large language model. As you see, there's no knowledge graph here. Here, what's in here is a very convoluted and huge billions of nodes of this kind of stuff, right? In spatial architectures, it might be that it's not fully connected. Maybe this actually connects to two. Maybe there is an extra layer here that skips and go back and forth. But there's some complexity there, but that's all. These nodes. So this is your ChatGPT. There are multiple LLM architectures. This is how it actually started with transformers in 2018, I'm sorry. And you can, for example, get here, the cat eats a, and then if you have learned to associate between one language and another, it can actually do translation. That's machine translation into another language. And another example, it is to classify a sentiment. For example, you have input text, I think the vacation is okay. And then the context is awesome, the sentiment is positive. And then you're saying, okay, please classify the text into neutral, negative, or positive. The LLM learns how to do that because you have, again, trained it to do that. And then it says, you know what, this one is positive. The LLM, the large language model here, nowadays, is so powerful that there is an infinite number of instructions that you can give it and actually come up with the right answer. This is an ever-evolving field. This is a paper from 2024, I think early 2024. This is how it started with BART, GPT-1, etc. In 2018, again, transformers. Attention is all you need. The first paper, as you know, that came here, and it's like a landmark paper for our, well, for humanity, actually. It's for the field. And then there's an adaptive radiation. There's so many things that happen. So much money that's being put for all the right reasons in this field. There's a race going on, right? And you see how many different branches we now have. And today is even more. Now going into applications. So what is evidence synthesis? Well, all this information that we have, a sentence here, some data there, we can take them all in and create one source of truth. We can synthesize the corpus of evidence around something. And I love Wikipedia, so evidence synthesis is the process of combining the results of multiple primary research studies aimed at testing the same conceptual hypothesis to make the findings from multiple different studies more generalizable and applicable. Well, it's not just studies, it's everything, right? You're having a lot of information that's relevant to one specific hypothesis. Apples are great for inflammation, reduce inflammation. You take it from different sources, you're putting all together, and then you're having, yes, no, yes, 80% correct, whatever is the answer. These are some work that we have done in our lab. One thing you can do is look at different papers in a specific field, get the data, integrate the data, and then do a meta-analysis. In this case, we wanted to ask the question about IBS, saying, okay, about 50 to 70% of IBS patients, IBS is irritable bowel syndrome, they do not respond to low FODMAP diets. It's a specific diet that it is the standard of care right now. So why is that happening? Is it random? Is this something in our genetics? Is it something else? So we said, okay, let's take the data from different studies that they have microbiome data on the patients, as well as the clinical outcome before and after, right? Clinical score. And then let's see if there is a pattern there. So we used AI to integrate and then figure out if there is a pattern. And what you see here, and this is the severity before the diet, and this is the severity of IBS after. And you can see that there are different groups. Some that they have higher severity before than after. So there, if you are here, diet is good for you. If you are here, okay, it's okay. Maybe it's a little bit bad, it's good, but basically it's inconclusive. And if you're here, actually didn't do anything, it can actually even hurt you. So what we did after that, and this is not AI, so I'm not focusing on this paper, but what we did is like actually going deep and figuring out, okay, what are the pathways, what are the genes, what is the microbiota, what are the microbes in there? And we found out that there's a specific pathway related with methane and specific biomarkers that you can actually test for that I can predict even before you start a diet. And this actually takes 3 to 6 months. If you are on the diet, you'll not know. You have to go. But I can predict with very high accuracy, it's 0.8, like 80%, 85%, if the diet will work for you or not. So you can triage. You can say, hey, you know what? Don't do the diet. Get some butyrate, get some other, or do the diet. This will be great for you, right? So you can see how evidence synthesis can actually lead to something actionable for our health. This is another work in our lab with Jason, who is now in TikTok from all places, and Avneet, who is in another startup on alternative proteins. Here, said, okay, good. Can we discover new stuff? Not only, previously was more about methodology, figuring out what's happening there. Here, can we discover new stuff in terms of genes, proteins, etc.? So we got all this data, again, 10 sources, 650,000 associations about E. coli. We put it in a knowledge graph. We constructed an automated knowledge graph. And then we applied something that's called knowledge graph completion. We actually asked the AI, find what connections could there be based on that graph, but we don't know it yet. Tell us, what are the genes that may lead to antibiotic resistance? Because antibiotic resistance is one of the biggest challenges that we're having here in terms of health. And what happened is it led to some predictions. So out of this, we discovered 15 antibiotic resistant genes that we validated in the lab. And we now know how they actually operate. Okay, so previously we saw how we can use it to create new treatments, interventions. Now we can see it, how we can use it to actually discover biology and our world. New discoveries. Okay? So AI is doing two things. Either increasing productivity, and we're going to see what this means, or accelerates innovation. Okay? Accelerating innovation, that will be a case. Can you imagine going one by one and testing all these genes, how much time it will actually take, versus coming here and say, hey, these are the ones. These are the 30 genes you have to test, and 15 of them, actually, they were the right ones. Okay. So let's go to FoodAtlas now. When we started this work, we were looking at, okay, we want to find out what's in our food and how it connects to health. These were the issues we had. Lack of public identifiers, lack of verifiable references, limited metadata, limited coverage, manually curated, reproducibly and updated issues. Actually, if you are looking from the tens of thousands of chemicals that are in thousands of food, FDC Foundation Foods focus on 236 foods. Out of tens of thousands of foods, USDA Food Data Center, which is an amazing resource, has only 200 and 400 chemicals. That's it. Of course, our food has much, much more than this. FoodDB is one of the most notable resources that has been created by David Wishart in University of Alberta. An excellent researcher, brilliant. And it's the number one, like even now, if you say, okay, where do you go? You go to FoodDB. Well, FoodDB is unpublished. There's no publication around FoodDB. And when we were looking, I said, okay, great. Well, out of the 70,000 connections, I think 63,000 are computationally derived, and about 1% of the association have references. So you cannot really trust the information. Again, it's one of the best resources out there. I don't want to, I want to undermine or even, it's a very significant resource. And it's our benchmark and standard whenever it is, because again, it's very practical. But still, you see, there's a reproducibility and a confidence issue here. Can you really make new treatments? Can you really put yourself into trusting the chemicals and the foods and whatever we tell you if this is the standard of truth? Okay. And last point is, while food chemical associations with support evidence presented in DBs are in the thousands, it's estimated that more than 1 million reported in public literature. Okay, so there are much more out there. For that reason, we created FoodAtlas. FoodAtlas version 1, which is what you see here. It looked at all the papers out there. Automatically, we created an AI, basically. We went out there, took all the papers. It was able to recognize what is a food, what are the food types, what is a chemical, and how are they associated, and then put it in this huge graph with 250,000, 285 when we started. Now we are printing 250,000 food connections. This is where it gets a little bit more computer sciencey. So the way that it operates is you're getting the food names in, for example, avocado, lettuce, etc. You generate the premise hypothesis pairs. You update the training data that you have, and you have an iterative process where you are creating those hypotheses. You are calculating the probability of the hypothesis. Apple contained epicatechin, for example. That would be a hypothesis. And then you predict, and then you validate, and you do it multiple times. So the model, the AI, is becoming good at recognizing what is true and what is not. This is a key principle when it comes to AI. People may think that it's a black box, it's magic, you put it in, if you have good training data, it will just generate the output. In my career, it has never worked like that. Okay? It's always about iteration, iteration, iteration. It's always about trials, failures, and at the end, after many, this N here can be 5, 10, 50. Here we had like some, again, undergraduates, and they were reading like hundreds of papers each time and created data sets of 1,000 to 2,000 samples. I don't remember, again, it's been like 2-3 years. But we're talking about 1,000 to 2,000 associations. Like they were going manually, creating this benchmark, going in, retraining the model, validating, creating another benchmark, doing it again and again and again. And if you go to the paper here, you are going to see how AI is learning through this process, how it's becoming better and better. Okay? This one, and again, go to the, like, if you are interested, please go to the paper here. We compare to the ChatGPT of the world. We're comparing to other algorithms, etc., and it's beating it. It's not beating it because architecturally it's better. It's beating it because it's very specific for this task, and we had to retrain it in this iterative fashion. Okay? So this iteration I'm talking about is extremely important. Okay, some numbers here. This model extracted 230,000 food to chemical composition relationships. Again, this is food contains X chemical. From 155,000 scientific papers, with 106,000, 46% of them never been reported in any published database. The world is publishing stuff out there. It's a tremendous amount of money, time, and energy we spend, and we really need it. 46% on what this model learned was never in a database. It's hidden out there. How many papers can you read in a day? 150,000? How much time will it actually take you? We see actually why we need this kind of tools. We need a way to organize all this and give it as a summary, or a way to actually find our ways in and be able to use this knowledge for new products, for new interventions, for new treatments. This is FoodAtlas version 2. What I showed you was about 2 years ago. Now, the large language models have become so powerful that we're asking, it has shifted from custom architectures to asking it the right questions. Until now, it goes, OK. By the way, what's the time? I'll have another 20 minutes. OK, good. Before that, it goes, OK, I'm going to be a computer architect. I'm going to have these layers here. I'm going to tell you this way. These are the equations. This is the math, etc. Nowadays, nothing. It's actually depressing. If we like math and all this kind of stuff, it wouldn't, I mean, unless you are in one of these companies with billions of budgets, right, and many people, right? And even you have to be really, really good and lucky to be in the team who actually goes deep in the architecture. It doesn't matter so much. What it really matters is to be able to interact with the tool, the LLM, that has been trained by OpenAI, from Meta or whoever, like Google, Gemini, and all that. They have spent hundreds of millions to just train it. Okay, and even a question there, just as to optimize a question or a type of question in those Gemini, that would be 60 engineers and $50 million for a year. That's one question, right? There's no way we can actually do that in an academic environment, right? But what you can do is, once you take those pre-trained models, you learn how to interact with them. Basically, it's like a human. You're learning how to ask you the question in a way that you understand, in a way that you are going to give me the outcome I want, the output, the result. This is where most of the engineering actually goes these days, prompt engineering. And there's a lot of plumbing and engineering around, how do you connect it, make sure that it doesn't hallucinate too much, and all this kind of stuff. But this is the big shift from 5 years ago, even 3 years ago. So this is where you use this much better information extraction by using these very powerful models now. And we, on top of food and chemicals, we now also have flavor, right? So chemicals to flavor, as well as chemicals to health. Okay? This is how it looks like the composition. We have glycans, lipids, ions, etc. And then you have chemicals. This is how the representation is in the knowledge graph. Chemicals contain foods. Food contains chemical. The chemical has a flavor or treats or worsens a disease. Okay, just to have an idea how you create that knowledge graph. So, okay, now that we have this, what can we do? Preliminary results just came out of print, like I think my students did over the past 3 months. Well, you can ask, what are the food classes based on composition? So what are the groups of foods that have similar composition that may tell you, okay, maybe they have similar bioactivities? Maybe I can substitute one from the other if they're in the same sack, in the same group. And if you see, they do preserve the structure of dairy, fruit, legume, etc. Although you find some outliers. Here you have a fruit that's in the middle of plants of nuts here, for example. I don't know what it is, right? But it's interesting that if you're looking at the chemical composition, structure is preserved. That's observation number 1. Observation number 2 is, yes, but you do have outliers. And you do have uncommon, unexpected members of those groups. Second question we can ask, are the food bioactivities the sum of their chemical parts? So if I would say, oh, we take apple and we tried and see the inflammation markers into 50 individuals. Okay, good, nice. Now let's do the same with the chemicals within. If we decompose the apple to its chemicals, that we know at least, do we have the same result? If we say that it has 30% reduction in inflammation markers, will the chemicals, the sum of those chemicals, have 30% reduction? Well, not really. Not really. If you look at the correlation, and again, this is antioxidant score from chemicals, this is antioxidant score from food in the literature, there is some correlation, right? But it's not really good. What does it say? What does it mean? It means that we need to explore more and figure out more about the molecular composition of our foods. And this is in collaboration with Periodic Table of Foods, funded by the Rockefeller Foundation, American Heart Association, an excellent group that what they do is looking at 500 foods to start with and go deep in terms of molecular composition, right? We need this kind of data sets in order to be able to know more about what the food is doing for us and our planet, and in terms of sustainability. Another question would be, what are the foods that are protective for different diseases? Okay, so you can actually look at this and find clusters around it that, hey, you have this cluster here that it's not good if you have digestive system problems, but there's another, let's say, good one, F here, protects against peripheral nervous system, etc. So again, now you can cluster foods and you can pick and substitute even from your diet foods that they have significant and similar bioactivities. You can do the same by focusing on disease. Then, okay, I want to have inflammatory kidney disease, etc. If I take kidney disease here and I look what are the different foods, again, now I'm flipping the problem into your head. Instead of food to disease, I'm looking at disease to food, similar results. You can go deep. Each of those points, it's not just a point, it's not just data, actually it's chemistry behind it. So you can see here the source, grapes, for example, how they're actually leading to different bioactivities, muscle growth, anti-inflammatory bioactivity, etc. By looking at now the chemicals that now you have it from the papers. Last but not least, it's one thing to talk about food, a different thing to talk about diet, right? Meals. We don't just eat apples, one food, but it's a group, right? It's multiple things together. So here we ask the question, okay, good. We're taking what, can we substitute one thing? Like minimum sacrifice, minimum friction, because we don't like to change our lives, right? We like what we like, and we know that, right? And this is the biggest issue. I mean, I have this issue. I love sugar, I like chocolate. You tell me like, look, I mean, you're gonna live 5 years more, but you are not gonna eat chocolate anymore. I say, the hell with that, right? I'm gonna die young and really happy, okay? But is there something there, if you're looking at all these diseases, right? And this is like the meal that we are having for breakfast, for example, is there, if I substitute something that it's not gonna be a big sacrifice for me, because especially if you know what I like and I don't like in terms of flavor, or in terms of how much I can support, how much I can pay, right? And I have a better bioactivity, it make me to live a little bit longer, then why not, right? Why not actually providing that information to our society, to us, so we can make the smart choices? And even more, I'm pretty sure that companies will actually know that, will want to know that, because this is an amazing claim to do. And here you can see the bioactivity. This is one substitution that we did, right? Oh, the way we proposed that, we have the 1 million recipes, we have what America eats from USDA, etc. We took all these meals, all these food recalls, we analyzed them, and we made one substitution on it. And then we looked at how much better the meal will be in terms of bioactivity. how much more protective it will be. And the results are amazing. Now, this is without taking into account flavor, right? Or other attributes. If you are to go on be very practical, you need to integrate that, and it should be personalized for all of us. But this is more of a proof of concept that this is a direction rather than a solution. OK. We're getting into the last part of the talk, another 3-4 slides. First of all, what I present today, there are many tools that they have come into, they're now out there, that they're doing this kind of evidence synthesis, some of them for academia, some of them for companies. None that it is excellent, that I know of. OK? So it is impressive, but still we need a lot of work here. Issues that we have with tools like that and general AI, bias, reproducibility, and performance, right? We've all heard about hallucinations. That's a big issue. Trust and transparency, OK. So AI will tell you it more, I don't know, it more grapes. Why? OK, why should I trust you? Like, show me the evidence. AI is still not very good. Now it's better than 2-3 years ago. And there are different engines like Perplexity, et cetera, that's focusing on this interpretability and justification. But still, we need more to be done here so we can trust it. Time and cost. Again, to train some of those large language models, it's prohibitory for, I think, 99.9% of the companies and the population, right? It's only big companies that can do that. It takes too many, like tens of millions of dollars to hundreds of millions of dollars. And we still are not there in terms of training. 2 slides that I put in terms of where we're going. One is that we're not the first to actually talk about this. People are thinking of how to integrate AI into public health. And we have been, like APHIS has been in 2 conferences in national academies this year, right, Steve? Right, this year, 2 conferences, one in February about evidence synthesis in nutrition, and another in AI and agriculture on actually figuring out how to improve public health with AI. And it's already happening. So for example, this is the old model of how evidence synthesis is working. You have like these professors and experts in different agencies coming together from hospitals, et cetera. And after 5 years, 6 years, they may put a review on what is the best practice for kidney treatment, right? Look, all this in order to have this point of the report. Well, nowadays, it's actually, especially this has been catalyzed by COVID. We wanted actually very rapid reproducibility and very rapid iteration and outputs. It is much more iterative, and let's get things out with AI assisting the final result. So what does the future look like? Well, today we talked about food. We talked about AI, how we are building it, how we are applying different questions. But it's not just the food. Food is food, and what it does for us, it's only part of the equation. To have that food, we need to know how to process it right. We need to know how to actually cultivate the crops, crop management. We need to know what seeds we're going to put in, like how we're going to modify or breed or change the attributes of the seeds. So they are drought resistant, they have more iron, whatever it takes to create this product. So it is a continuum. And this is what APHIS is about. It's not a micro project here and there. It's not only one vertical. Let's look at food and health and only food and health. Well, actually, in order to produce that apple, go back to the farm. Go back to the university that created the first seed. So if your goal, as Steve said, is a healthier society and a more sustainable planet, figure out how to do that, right? For example, now, because of PTFI, we know what's in our apple. And again, it's USDA that pioneered all that, and the best data still is USDA. But what PTFI has done is saying, OK, good, this is the apple from 100 apple farms. Great. These are the composition of apple, different replicates. But now they have also taken soil samples and regenerative practice or standard practices in the farm. So for the first time, you can say, what is a healthy apple, a good apple for our health? And what are the practices in the farm that's great for our planet? Less resources, more productivity, more quality. Okay? So this is the first data set, at least I know. And this is exactly what we need. We need to go and figure out how to make a tomato that people will buy. It's better for our health. It's more sustainable. It has better economics. And go for all those verticals and answer that question. What should we change? And you can see some of them here, right? I'm gonna skip that. The future is basically integrating the LLMs that you saw with the knowledge graph. The knowledge graph will give you more of the determinism and reproducibility. The LLM will give you this amazing back and forth and a way to be interoperable. Last slide. It's amazing what AI agents can do. What is an AI agent? You're taking an LLM and you are purposing it for something specific. It can create your calendar. It can figure out the weather. Okay? This is from a recent paper. This is how it's blowing up. AI agents, the market was like 3 billion a year ago. In 2030, in 6 years, it's going to be 50 billion. Okay, we're talking more than 10x. To give you an idea, synthetic biology, it's 16 billion after 20, 25 years of development. And it's going to be 30 billion by 2030 something, not even 2030. 2x in a bigger duration. Like this is taking over the world. Okay, so this is what we're talking about. Future is how can we play here? How can we make those agents to be very efficient for what we want? And with that, I would like to thank this work has been, again, only possible because of our staff and our students and postdocs. And I would like, this is the website of FoodAtlas. If you'd like, you can go and try and see what's in our food. Thank you very much.
All right. We have some time for questions. I have a microphone here that feeds into the Zoom meeting. So if you have a question, raise your hand. We'll hand you the microphone. Come over there first.
Hi, I'm John O'Donnell. I'm an alum in the chemical engineering department. Thank you for the insightful talk. And I would just love to hear more of your insights. When I look around, it seems kind of rough for creatures of lower intelligence. So, and it seems from the talk and everything around me that actually we're headed for a world where machines will have a higher intelligence than humans. So how do we handle that?
That's a great question, and I don't have the answer. But it's an existential question, right? I mean, how do we handle that? First of all, let me say that everything that's happening, we were expecting it. There's nothing new for us, for people who have been in AI for quite some time. This is just standard. It's just that it was accelerated. We wasn't expecting it so fast. We're expecting like 5-7 years later. Okay, so that's something that took us by surprise. At least the people I talked to. Second, let me say that exactly this question is in the minds of everyone who knows about AI, because we see consciousness is coming. AGI, artificial general intelligence, is coming. We know that. Again, it's not an if, it's when. And the problem is, like we thought we have enough time to actually talk to put the right safeguards, and that's something that we are concerned. So the question is, what do you do? Well, we need first of all to be eyes open and tackle it now. There has been, somebody told me, and I haven't heard that, but somebody told me, a journalist told me that Jeffrey Hinton has called for a portion, a pretty big portion, 20-30% of different companies' profits to go actually for safeguarding and making sure that, you know, we are AI in the future is not harming us or is not taking our place. I think that's a great idea. Another thing that I'm thinking it should happen is we should actually use AI for our own evolution too. We should actually make sure that we are becoming better and better by using AI. And I'm not talking about genetic engineering per se, but doing something so we co-evolve as AI evolves. I hope not, by the way. I hope not, we don't need that. But it might be other ways of actually doing it.
All right, question over there.
Thank you for the talk. My question is, how do we incorporate kind of like the social aspect of food and food procurement to all of this? Like, if we find out cacao has all of these great health benefits and we're only looking at just the chemical composition, how do we then account for how cacao is grown, the impact on the laborers and all of that, so we're not, feeding into our same, like system of how food has been produced before?
Yeah, great question. It's a food system. It's not food, right? And again, AFIS is AI Institute for Food System. There's a reason we put food systems there. You're totally right. It's a system, and you need to see it holistically. Otherwise, you will miss out. And this is one of the problems we have right now in our society. They think they are doing a little bit here, and you actually will impact. No, the impact will be minimal because you need to see it to the continuum as we saw it before, right? So slowly but steadily, by prioritizing what matters, you start building this continuum and connect the dots that go from the seed, from the farm, to fork, to our stomach, right? And then maximizing your impact across those verticals. Together, the cumulative impact, not just a little bit here, because that will not work.
I had a more technical question, but I decided to switch to a more provocative question. So you hear people say, oh, AI will cure all diseases, diabetes, Alzheimer's. AI will create, understand the biology perfectly, and so on and so forth. We will live 150 years old, and so on. I'm curious about your thoughts on that.
Yeah. So it all depends. What can AI actually do that? Of course it can, right? What does it need? It needs to be able to interact with the physical world, has consciousness, a kind of consciousness, interact with having the inputs, so being able to have outputs, so be able to interact in and out, and do things really fast, right? So there have to be advances in robotics, in automation, in other fields, in order to be able to AI the brain to actually operate. It's not just the brain, it's the body too, right? We need the body to be on par. It's not yet, okay? Thank God it's not yet, by the way. Okay, so can it do it? No question, right? How many years it will take? I have no idea, okay? Now, I don't think, so people are saying, oh, biology is so complex and AI will never figure out the biology. And I'll say, so what? Yeah, okay, but this is not the right question. The right question is not whether it will figure out biology. The question is, it doesn't need to figure out our biology to be able to really interact with us and really impact our lives in a good or a bad way. We need to think about that. We need to think what would be the easiest path and the fastest path that we need control so it doesn't, in a negative way, impact our lives. And this is not the AI learning about the biology. It will take much more time than other things that will be much faster. So I think that we need to focus more on that question versus what is possible. And yes, it is possible to learn the biology, but it's like further on. I have other issues before going there.
All right, we have time for one more question. Oh, yeah. Yeah, go ahead and read it off. Yeah, let me bring it over to you.
So do you use any mechanism to check the accuracy of the information in the papers before the trading process to avoid misinformation? Not all the compounds reported are 100% correctly annotated.
Yeah, now that's a great question, technical question. So there are multiple ways that we do that. First of all, we are figuring out there is a trustworthiness score that we are assigning based on the publication. So for example, if something you see in Nature Science, it's more trustworthy than a Greek journal of who knows what. So that's one, and there are actually algorithms that they look at how many a paper or a journal, how many things, just to give you the algorithm, how many times it reports correct stuff versus incorrect, and there is like a iterative, that's one algorithm. There are multiple algorithms that you can apply to make sure that this is happening. Not all information and all sources are equal. And then after you do that, there's something that's called the wisdom of the crowds. Basically, and you have seen, like, do you remember Who Wants to Become a Millionaire, right? And it's impressive whenever they ask the crowd, actually the crowd is pretty correct, right? So you can do the same. If it's reported by more sources, even if those sources are not, the high, like you can actually trust that more. And there are models that they do that. So by doing this too, having a structured approach to trustworthiness, you're able to filter out information that will be just noise. Once you do that, and this is the algorithmic part, then you go to the lab and you validate your findings. And many times we do that. Of course, you cannot do it for everything.
All right. Thank you very much.
Thank you.